Hello, my name is Higazi and I'm also presenting on behalf of Ana Cecilia Garza Gonzalez. Our research title is Assessing the Performance of Earth Ducts for Passive Cooling in Hot Humid Climates, based on the Oroville Language Lab case. Oroville is a township located in Tamil Nadu, south of India. We started off by looking at the climate data, and our first impression was that Oroville is very hot and humid, with high solar radiation all year round. We also observed that the soil temperature fluctuates between 24 to 33 degrees Celsius and becomes constant at 28.4 degrees Celsius after a depth of 7 meters. This speaks about the design precautions to be considered given that the ambient temperature on average is around 28 degrees Celsius. But why is this relevant to us? The design proposal for the language lab suggested that there would be an 8-meter high inlet tower which draws air into a 3-meter deep earth duct. Cool air is then moved from the earth duct into the rooms through shafts, where hot air is exhausted through a solar chimney. However, this is the building today. The inlet tower is only 2 meters high and is connected to the earth duct. Openings where connecting shaft and solar chimneys should be are covered with grills. So how can we move on from here? Our research was divided into 3 parts. First, on-site measurements and model calibration. Next, assessment of the design intent. And finally, investigating the potential of optimizing this system. The purpose of this phase was to get a better sense of conditions in Oroville. Data was collected to show how the current building performs and to calibrate the simulation models. The building is constructed of brick with lime mortar covering both sides of the walls. Our as-built model even included the extra openings reserved for the solar chimney and shafts. By calibrating our model, we learned that there are high levels of air changes due to infiltration, as well as a 1 to 4 Kelvin difference between day and night air temperatures. We also compared the data logged for the earth duct and the classroom. The red line represents the earth duct air temperature and shows that it can be sometimes warmer than that of the room. We then asked ourselves, how would the building perform if it was completed as intended? We set up a model for the design intent using Transys 18 with the TramFlow feature. The graph shows the ambient and air temperatures during a hot week in May. The green line represents the design intent air temperature, showing warmer temperatures and less fluctuations throughout the day when compared to the as-built model. Moreover, we observed that there are less air changes and that the direction of the airflow is inconsistent throughout the day. We then split the system components as 3 variants to determine what the driving forces of this system are. From this, we learned that the large volume of the earth duct, its position, and the low temperature difference between it and the room make it the biggest driving force in this system. That and the soil temperature profile as mentioned earlier. We also saw that the inlet tower does not necessarily improve the system's performance. Knowing this, we then asked ourselves, would controlling the system actively help improve its performance? This led to our final variant, where we added an electric fan to our network to control the airflow amount and direction and remove the inlet towers. We maximized the air changes to 20 from 12 to 7 a.m. when the ambient temperature is cooler, and then limited it to a minimum hygienic air change rate for the rest of the day. Looking at this annual temperature profile graph, we see that controlling the system did not result in lower temperatures all year round, but reduced the potential of overheating when ambient temperatures exceed 31 degrees Celsius. This raised another question if increasing airflow further at the designated hours would help in reducing the room air temperature. To settle this, we ran a new variant doubling the maximum air changes to 40 to see if it would reduce the room's air temperature. As shown from the graph, this assumption was not true, showing the strong impact of the high ambient temperatures. We learned from this experience the importance of understanding the local climate with respect to the building typology in question before proposing a climate concept in design, as they have to be tailored accordingly. Including the fan aided the system's performance, but external factors such as ambient and soil temperatures limited this. While the proposed system showed limitations, the studies showed how thermal mass and airflow controls have a great potential in improving thermal conditions in hot, humid climates. Finally, it is noteworthy to mention that this research was conducted as part of the annual project for Transsolar Academy 6 in 2019. We are immensely thankful to everyone who supported us during our time at Transsolar. Thank you.